All right, welcome to the Math 2144 Calc 1 exam review. In this, we're just going to kind of go over the exam, the first exam from last semester to kind of give you guys some practice for your upcoming exam. So as far as this first question goes, you have the average rate of change of a continuous function y equals f of x over this interval is 0.4, so I'm just going to write average rate of change from 4 to 9. We know that's 0.4. And then we're given f of 9, or asked to find f of 4. Now, as far as this question goes, first I'm just going to kind of write out the equation for that average rate of change. That would be f of 9 minus f of 4 over 9 minus 4. Now, because we're asked to find the value of one of the endpoints, we will be able to determine what that value was. Now, going ahead and plugging everything in, I would have 0.4 equals 1 minus f of 4 over 9 minus 4 is just 5. So that means if you multiply everything by 5, 2 is equal to 1 minus f of 4, which means that f of 4 is just negative 1. So that will be C here. Moving on to number 2, we're supposing that the limit as x approaches a of df dx exists. Which of the following could be a graph of the function y equals f of x? So in order to determine that, we're just going to kind of go through each graph and think about whether or not that limit would exist, right? So as far as our graph of a goes, we can see that on the left over here, our derivative is positive, but to the right of it, our derivative is negative. Now, that would mean that the limit would not line up between the left and the right hand side. If those aren't equivalent, that means that our limit does not exist, D and E. Moving on to B, we kind of want to think about the same thing. Over here, right around A, on the left hand side, we're decreasing. On the right hand side, we're increasing. Again, because the limit there, it doesn't line up on either side, that means that this limit does not exist. As far as C goes, we have it being evaluated at this point right here. Because our function is continuous there, we don't have any cusps, we don't have any sudden discontinuities. This one's absolutely fine. That limit should exist. On to D, here we have an asymptote. But if I think about what's happening to the left and to the right, on the left-hand side, we're increasing up to that asymptote. And on the right-hand side, we're decreasing down from it. So because, again, that doesn't line up on either side, that limit will not exist. On E, we know that because this is a cusp, we can't take the derivative there. But again, on the left-hand side, we're decreasing. On the right-hand side, we're increasing. So that limit will not exist because it's not, the limit isn't, or the derivative isn't 0 there, and we can see it very clearly does not line up at that point. On to F, this derivative is indeed, or I guess we can't take the derivative, we can't evaluate the derivative here because it's a point discontinuity. If I think about my function, it's decreasing and slowly getting closer to 0, and to the right, it's coming up from 0, and we don't really have any discontinuities there, so this limit is also fine to take. And the difference now just between F and, let's say, E, because it does change whether or not it's increasing or decreasing on either side, is that there's that cusp here. So if our graph was continuous and differentiable, which means no cusps, no asymptotes, nothing like that, then the limit does exist, like in F. But if there is a cusp, like in E, or there's an asymptote there, like in D, that means it does not exist. So as far as the ones that we said are fine, that is really just C and F, which means that our answer will be graphs C and F only. On the next question, we're given a picture of a vase that's being filled with water. V represents the volume of water in the vase, and H represents the height of the water in the vase. Now we're asked to determine which graph could represent the function dv dh, which is the derivative of V with respect to H. So what I'm going to think about here is that if I have a little bit of height, so if I start here, go from the bottom, we add that much height, our volume would change by this little area, right? Now if I go up a little bit further, just the same amount of height, our volume is going to increase there. Do the same thing. You can clearly see it's going to be greater, right? So I know that the rate of change should be increasing up until we get to about, let's say, over here. Now here's where it should max out, somewhere around that. And then as we keep going a little bit, we'll see that it starts to decrease. The walls start closing back in on our little differential area. So we know that it should kind of start increasing and then decreasing again. Now when we get here though, notice that the walls are at a constant length, or they're at a constant location, right? So as I increase here, I keep adding the same volume over and over again, which means that there should be no rate of change because the area of these differentials should all be equal. So once I have an increasing and decreasing portion, I should just have a flat area. If we look at our graphs, that is exactly what graph D is. On to part 4, we're given a limit definition of a derivative. We're asked to determine which function we're taking the derivative of here. So I guess what I would write out here is that we're using the definition limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So you've probably seen this with limit as h goes to 0 of f like this. These two are essentially operating the same way. They're just a different way of expressing the same concept. So if I go over here, right, this has our x plus delta x inside of it. So that, to me, says that this should be our f of x plus delta x, which kind of then says, okay, well, then this would be our f of x. If we look down, that is choice B. There we go. Now on to part 5, we're asked to suppose that if a function y equals f of x has a jump discontinuity at an input value x equals a, which the following statements must be true if the function f is continuous at all other inputs. So I'm going to go ahead and set up some axes so that we can sketch some graphs to kind of think through what we're given. I'll go ahead and mark a point. A could be anywhere, it's kind of arbitrary. First, between A and B, we're told that A must be defined or undefined. Now, I can draw examples of both. I can draw examples where both of those are contradicted. So like, let's say if this was my example, I have a hole there, a hole here, going on. This would be an example that satisfies what we're given, where it's undefined. So we know f of a doesn't necessarily have to be defined, but if I draw it like this, where I have a point up there, I have our jump discontinuity still, f of a is defined there. So we know that a is also not true. Now I'm going to kind of start from the bottom. I'm going to just keep rolling with this graph. So we're told that the limit as x approaches a from the left exists, or it exists from the right but not both. Here we can clearly see we can evaluate on either side, so this one cannot be right. As far as E goes, we taking a limit from either side, say this is like 1, 2, 3, we can see that, clearly, the limit from the left is not what f of a is, because that's up here. The limit from the right is not what f of a is, because again, that's right there. So E can also not be true. D, again, it says that one of those must be true, where the limit from the left or the right must be f of a. Here, not really the case, so we know that's not true. So that leaves one answer choice left, which is C. And looking at our graph, we can see, okay, well, the limit from the left does exist, the limit from the right does exist, and they're not equivalent. So that's perfect. There we go.